We now know how to deal with straight lines in three-dimensional space, but there's another type of flat object of infinite extent that you can have also. You can have a plane in three-dimensional space. We're going to need to have some way of describing the orientation of the plane. The plane itself contains a great many straight lines, but there's only one straight line direction that's at right angles to a plane. The way that we'll describe the orientation of the plane is to give a vector that is at right angles to the plane. For instance, this situation, or this one, or this one. There are many planes that are at right angles to the same vector, so telling you the right angle direction vector n is not enough information. I have to tell you something more. If I also know an actual point that lies within the plane that I'm interested in, then out of all parallel planes having the same right angle direction, I will have singled out one of them. So knowing a right angle vector and knowing a point in the plane should be enough information to completely tell me all about the plane. So I'm going to think of looking at a plane that contains the known point x0, y0, z0, which is at right angles to the vector n, which for convenience I'll call its components a, b, and c, not to be confused with the a, b, and c that we were talking about with straight lines. Those were components of a vector that pointed along the direction of the straight line we were trying to think about. This is a vector that sticks up at right angles out of a certain plane. Let x, y, z be any other point in the plane. If I form the vector from the known point to this other point, this is a directed line segment that lies completely within the surface of the plane. Therefore, it's at right angles to the n vector. The vector in the plane has components x minus x0, y minus y0, and z minus z0. For that to be at right angles to vector ABC, the dot product of these two vectors should be 0. This kind of an equation, a linear equation that relates the variables, is going to represent the equation for my plane. The significance of the numbers are the coefficient of the x, the coefficient of the y, and the coefficient of the z parts are the components of the vector at right angles to the plane. When written in this format, x0, y0, z0 can be read immediately off as a point that lies in the plane. If it were advantageous, you could multiply all this out, collect the constant terms over on the right-hand side of the equation, constant times constant plus similar. I could just call that constant d or something. This is actually somewhat less informative than the first form because although I can just look at this and read off a, b, and c as the components of the n vector, it isn't instantly clear where a point is in this plane, as it was in this description. It won't be hard to extract such a point, though. In the analogous problem in college algebra, when you're given 2 points and want to find the straight line between them, you find something that tells you the direction of the line, namely the slope, and then use one of the points to produce the point-slope form of the equation. If I give you 3 points that are not on a straight line, my P, Q, and R here, the natural three-dimensional version of that question is, can I find the equation that describes the plane? All I need is a point in the plane, which is no problem since I know 3 of them, and a vector at right angles to the plane, which is a little bit of a problem. Doing the usual end minus start thing, it's not very difficult to figure out the components of the vector from P to R and that from P to Q. The reason that I want to do this is both of those vectors lie completely within the surface of the plane. If I take the cross product of those two vectors, I'll get something that is at right angles to P to R and also is at right angles to P to Q. It's going to be at right angles to the plane containing those two vectors. That'll give me one choice of my n vector. Based on this reasoning that we've just stated, I'll select one of my 3 points. I'll use point P. The vector x minus 1, y minus 0, and z minus 1, dot product with the right angle direction needs to be 0, and this immediately gives me the equation for my plane. As we've previously figured out, equations like this describe a straight line in 3-dimensional space. As a simple geometry question, let's answer this. If I give you a straight line and a plane, can I tell if they intersect anywhere or not? The equation x plus y plus 3z equals 2 represents a plane in 3-dimensional space. Now, there's a way that I can tell that I'll have an intersection point even before I do any calculations. A direction vector for the line is 2, 1, negative 1. A right angle direction for the plane are the coefficients of x, y, and z in the equation for the plane. So the vector 1, 1, 3 is a direction vector that's at right angles to the plane. If the plane and the straight line fail to have an intersection point, that means that the direction of the straight line must be at right angles to the normal vector to the plane. Unless we're incredibly lucky and the straight line lies completely in the plane, then we're not going to find any intersection points. Let's see how that can be represented in terms of the formulas. The equation for the plane is x plus y plus 3 times z equals 2. But on the other hand, if I want to be on the straight line, x is 3 plus 2t, y is 1 plus t, and z is 2 minus t. So rather than literally writing x and y and z, I'll write those expressions in terms of t in. Doing so, I find out that 3 plus 2t plus 1 plus t plus 3 times 2, 6, minus 3 times t must be 2. 2t plus t is 3t minus 3t. The t's cancel each other out. And 3 plus 1 is 4 plus 6 is 10. To make this work, 10 would need to equal 2, which is false. This is false no matter what t number you put into this equation. There is no way to make this and that true at the same time. I have a line that is parallel to and outside of the plane. As another example, let's think about trying to intersect this straight line with this plane. The components of the direction vector for the straight line are 1, 2, and 3. The right angle direction for the plane is 4, 5, and 7. When I do this dot product, the three things I'm going to be adding up are all positive. The dot product, therefore, is positive as well. This tells me that the direction vector for the line is not at right angles to the normal vector to the plane. I should have a line intersecting a plane in a single point in this situation. As predicted, there's a single t-value that will work. If I take this t-value and put it into each of these three equations, I can actually find the x, y, and z coordinate of the point of intersection. Another geometry question that we can now answer is, if I give you two planes that are not parallel, and these certainly are not parallel, the right angle direction to this one is 1, 1, 1, while that one has right angle direction vector 2, 1, 3. Those point in different directions, so the planes are tilted relatively to each other. When you intersect two such planes, typically you get a straight line as the intersection of the two planes. In this system of equations that I have, I'm going to see what it would mean if the z-coordinate were 0 in both of these equations. I'm thinking of having my line of intersection and seeing if it ever runs into the xy plane. It's possible that it doesn't, but maybe it does. If it doesn't, next I'll try setting y to 0 instead, and if that doesn't work, I know that the straight line of intersection has to have some place where x is 0. So to get a v-vector for my line, I need to know a direction that is at right angles to that, and also at right angles to that. One of the things that we saw in our previous work, though, was that if you have two vectors, neither one of which is the 0 vector, as is the case here, and you form the cross product, that's at right angles to both of the vectors individually. So I'm looking for a vector that's at right angles to that and at right angles to that. I'll just form the cross product of the normal vectors. I'll call the two normal vectors separately vector n1 and vector n2. Form the cross product in the usual way. A direction that my straight line is going to be parallel to is this direction, and since we have a point on the straight line of intersection, we can now write down the equations. X is the x-coordinate of my known point, -3, plus that number times the parameter, plus 2 times t. Y is the known y-coordinate, plus that number times t. I should probably write 7 plus -1 times t, but everyone just writes 7 minus t instead. And z has value at the known point 0. This component's -1. 0 plus -1 times t. Z is just going to be -t. These are parametric style equations for the straight line formed by intersecting these two planes. In the next video, we'll look at two different geometry problems. In one, I have a plane and a point not within that plane. I'd like to know the perpendicular distance from the point to the plane. Also, if I have a straight line in three-dimensional space, I'd like to be able to find the perpendicular distance from a point that's not on the line to the line. Again, I'm trying to make these current video's short, so I'm going to stop right there. I hope everyone's having a good day. I'll talk to you again soon.